Okay, keeping in the theme of some of the talks yesterday, let me talk about projective space. So this is just a nice example of gluing, and it'll come up again a little bit later today when we talk about properness. So let's begin with the most basic example of analytification. So K is our non-Archimedean base field, and ANK analytic. This is going to be, well, it should be characterized, of course, as any good construction by some abstract property that we can think about independent of the construction. So this should be the universal space equipped with rigid space X, equipped with an ordered n-tuple of global functions. In fact, they'll be the standard coordinate functions, but the construction is relatively straightforward. What we do is we consider unit disks, closed unit disks, that I'll denote dj. So these are, maybe I'll write bnk for the closed unit polydisk, B for ball. So these are all the space associated to a Tate algebra, indexed by j greater or equal 1. Psychologically, you want to think about these as a growing family of disks in a space that we're going to construct by gluing. And the way it'll work is if we think about this as having coordinates, this will be k brackets psi 1j up to psi nj. And then we imagine putting dj into dj plus 1 by sending the ith coordinate psi I j plus 1 should pull back using the universal property of Tate algebra to c times psi I j, where c is some initial choice of constant whose absolute value is between 0 and 1. And we want to think about this as being something like the disk of radius, the polyradius absolute c to the minus j. And so if we embed one unit disk into another by basically c scaling on the coordinates, then it's not too hard to show, for example, that this can be glued in an appropriate sense. You get a very big space, and in fact, it has the required properties. And more specifically, under this gluing map, you see that psi I j plus 1 divided by c to the j plus 1 goes back to psi I j divided by c to the j. So this is a compatible system. If we call this thing maybe psi I by abusive notation, we see that this particular function on this unit ball pulls back to the corresponding guy on this unit ball. And so therefore, these psi i's, in fact, are compatible with change in j. And so these give rise to the standard coordinates on the gluing. Okay? And so that's rigid analytic affine space. Having done that, you can then try to mimic other constructions in algebraic geometry. For example, you could try to construct, I'll just say very briefly, example, you could try to construct rigid analytic projective space, right, in 3 different ways or more. So one way would be you would glue together n plus 1 copies of affine space by the standard formulas on the usual overlaps. I should mention in passing, one has to, of course, prove, but it's not difficult using the maximum modulus principle, that under this construction, the underlying set of this is the set of closed points of the algebraic affine space, and any Zariski open subset of algebraic affine space gives rise to an admissible open set. Although, of course, it's defined by the condition that a certain analytic function is not 0. So it's in some sense a very large kind of open set, very different flavor from these kind of affinoid domain conditions that are defined by non-strict inequalities. In any event, Zariski opens in here do give rise to admissibles. Zariski covers do become admissible covers, and therefore we can mimic gluing constructions in algebraic geometry to construct projective n space by gluing n plus 1 affine spaces along the standard Zariski open hyperplane complements. But you could also imagine constructing this rather than gluing affine spaces. Perhaps you might want to just scale the coordinates, so to speak, and just glue n plus 1 closed unit balls instead. So we'll come back to that point of view later, but I just want to mention by way of segue that another way you might want to think about projective space is it should have a universal property in terms of n plus 1 tuple of sections of some line bundle, similar to the universal property in algebraic geometry. So maybe you might want to ask, you could make by gluing, or perhaps by universal, think about it in terms of some universal property. But in order to make sense of the universal property, you have to define what you mean by a line bundle on a rigid space. And so that more generally, that leads us to the question of how to make sense of coherent sheaves. So now we test out this, which of course is too big, unless yeah, you see? So, okay, well, there we go. So much for that. All right, so that said, is this distracting that it's so big? I don't know how to. It doesn't exactly shrink very much. Okay, well, you can enjoy that. And now we're going to go on to discuss coherent sheaves. Well, I would, except that I'm going to have space problems. Because, you see, here I could use one piece of paper. Well, anyway. There it is. So otherwise, I'll keep having to look up and back and run out of space, and I'll get hopelessly confused. Which reminds me, so I should apologize. Both times yesterday, I completely forgot to thank the organizers for the invitation to speak here. Thank you. Especially coming from a place that has winter, this is very nice. All right, although not as bad as in Michigan. Okay, anyway. All right, so let's talk a little bit about coherent sheaves. So in algebraic geometry, there's a very nice dictionary in the affine setting between Noetherian things, between finite modules and certain kinds of nice sheaves. And in fact, Kiel extended Tate's methods to develop a similar dictionary in the rigid analytic case. So let's suppose, to get started, A is a k-affinoid algebra, and M is a finite A module, so a finitely generated A module. And then the theorem of Kiel, so Kiel showed that if to every affinoid subdomain, so this is an affinoid subdomain in the rigid space for A, an affinoid subdomain, you associate the module tensor over A with A sub U. Okay? That this assignment, much as this sort of satisfies conditions as in Tate's acyclicity theorem, recall Tate's theorem said that was just the case M is A, that the assignment U goes to A sub U satisfies the required check exact sequence gluing conditions if we consider the covering of any affinoid subdomain by finitely many others, that you can cook up a check complex and that it's exact. And in particular, a global function is determined by gluing along the elements of some A sub U's for finitely many U's that cover the entire space. And Kiel showed the same exact thing holds. Well, actually, in this case, it's fairly easy. The hard part is what comes next. That we do have this nice construction that does satisfy the kind of sheaf axioms for the coverings of affinoids by finitely many other affinoids. And so therefore, this globalizes, so to speak. This can be promoted to an OX module that we call M tilde. Okay? And M tilde has the property, again, that M tilde, among other things, M tilde of U is naturally identified with M tensor AU for all affinoid U in the space of A. Okay? So this is very similar to the construction of coherent sheaves in algebraic geometry, and it does have a very nice universal property that I'm not going to formulate. It's in the notes, that basically says that these are precisely the sheaves that are determined by finite modules of global sections. The interesting part for real globalization purposes, going beyond the affinoid case, is Kiel's answer to the following non-obvious question, which is, if I give you an OX module on an affinoid space, so here X is SPA, if I'm on an affinoid space and I give you an OX module such that on finitely many affinoids that cover the space, it arises by this kind of a construction from a finite module over those affinoid pieces, then in fact does it have to arise globally from a finite module? Or put another way, is this particular construction checkable locally on the space? And so Kiel showed this is in fact true. More generally, he showed that if X is a rigid space and UI is an admissible affinoid cover, and F is an OX module, then there are two equivalent conditions. So the following are equivalent. First of all, you could ask whether for every open affinoid, admissible open affinoid V in X, you have the condition that F on V is in fact of the form MV tilde, where MV is OV finite. Does it come from a finite module over the coordinate ring of that affinoid piece? And the other condition is, well, likewise, just for V equals U sub I. Okay? So whether or not you come from a finite module on the constituents of an admissible affinoid covering is equivalent to doing so on all affinoid coverings, and these kinds of sheaves are called coherent. Okay? So there's a very nice theory of coherent sheaves. It satisfies all the familiar properties from the case of local Noetherian schemes, and I just want to mention one of those properties in particular. I almost feel like turning this off. It's kind of just a big distraction. Sorry, I don't really know what to do about that. So let me just mention one very important remark. Coherent sheaves are much nicer than more general OX modules in the following sense, that if F is coherent, this is a coherent OX module, and S is a global section, such that S vanishes Sx in Fx. So if you think about the stalk, the limit over U containing X, F of U, if this vanishes for all X in X, then in fact S is 0. Okay? This is briefly explained in an exercise in the notes by using a little bit of commutative algebra. But the reason why I'm mentioning this is this assertion, this property of F, this is generally false for general abelian sheaves. And in case this seems very surprising to you, you have to keep in mind that the usual proof of this implication for ordinary sheaves on a topological space is to say that this condition of vanishing says that for every point there is some open, depending on the point, over which the section has vanishing restriction, and that those opens give you a covering of the space, and therefore by the sheaf axiom, the global section must be 0. But the problem is that if I give you an open around every point, there's no reason why the whole collection should actually be admissible. This is the whole crux of this concept of admissible covering, that you do put some kind of local finiteness condition on things, so that the standard argument doesn't apply, and in fact there are counterexamples. So this is just an important point to keep in mind. Okay, so that said, for coherent sheaves, one has properties very much like in the classical case, and let me just mention one nice example. This came up in Kedlaya's talk yesterday. You can construct, for any x to y, you can construct a sheaf of relative 1 forms, and in fact a relative de Rham complex that has many properties much like in the algebrogeometric case, and in fact the construction is almost the same. The only difference is that everywhere you see an ordinary tensor product, you put a little hat on top of it, okay? And otherwise it's exactly the same thing. So the modules of differentials are of course quite important in practice, but maybe a more concrete manifestation of the theory of coherent sheaves is to define the notion of a closed immersion in terms of coherent ideal sheaves. So we'll say that a map f x to y is a closed immersion if what? Well, for schemes, you use the general notion of a closed immersion of ring spaces, and then you prove as a theorem that these have a nice relation to coherent ideals. These things are not ordinary ring space. Well, they're not ring spaces at all. I mean, unless they're like one-point spaces or something stupid. And so to define a closed immersion, we'll just, in some sense, work directly with ideals on affinoids. So when do we say this is a closed immersion? We'll say this if, well, there are several equivalent ways of formulating it. Let's just say there is an admissible affinoid covering, UI, let's say UI equals the space of AI of Y, such that if I take the preimage, of ui, that this is again aphanoid, in fact, bi, where the map on coordinate rings ai to bi is a surjection. Okay? So that's one way of making the definition, and then by using the theory of coherent sheaves, you can actually show it's equivalent to saying for all aphanoid open. Whenever I say aphanoid open, I mean admissible aphanoid open. U equals space of A. In Y, we have that the preimage of U is again aphanoid, where the map on coordinate rings is a surjection. And it's a basic fact, hardly a surprise. It goes almost exactly as in the algebraic geometry case, that there is, in a very natural sense that's described in the notes, closed immersions into Y are in bijective correspondence up to natural notion of isomorphism with coherent ideal sheaves inside of the structure sheaf on Y. Okay? So you can classify closed immersions by, or think about them by working with coherent sheaves of ideals, which is to say coherent sheaves of modules inside of the structure sheaf of the target space. Okay? So that's a very nice notion of closed immersion. And again, if you, for example, if you start with algebraic schemes and a closed immersion there, and you sort of analytify, you will always get a closed immersion in this sense. And in fact, you can copy several other definitions. For example, you can define the notion of a finite map in a similar way. So I'll just say that you can define the notion f to y being finite similarly, which is to say, exactly as in algebraic geometry, we would ask that for aphanoids in here, their preimages should be aphanoid, and the coordinate ring map should be a module finite map. But a warning, there is no concept, well, you can define things however you want, but there's no reasonable concept of what you might want to call an aphanoid morphism, where you might say, oh, well, maybe I'll just ask that the preimage of every aphanoid is aphanoid. But in order for that to be a workable notion in algebraic geometry, you need to use the Serre cohomological criterion for affineness, that a quasi-compact separated scheme is affine precisely when the higher quasi-coherent sheaf cohomology vanishes. But this is absolutely false in the rigid case. There are examples discovered by Qing Liu of quasi-compact separated rigid spaces whose higher coherent sheaf cohomology vanishes, but which are not aphanoid. So there are some slight surprises in relation to results from algebraic geometry that you might have expected to be true. But for finite aphanoid extensions, everything works just fine. Okay? So that case is perfectly good. And let me just mention, since I've discussed closed immersions, another important notion is separatedness. And this, again, goes exactly as in the classical case. So we'll say that x to y is separated, or respectively quasi-separated, if the diagonal map, just using the rigid notion of fiber product, is a closed immersion, or respectively is a quasi-compact map. If you have never heard of the concept of quasi-separated, then just ignore everything I ever say about it. Just think about separatedness, and you won't lose anything. And again, quasi-compact means that the preimage of any quasi-compact open is admissible open, is again quasi-compact. Okay? So as I said, once we have the theory of coherent sheaves, we can sort of copy many notions from algebraic geometry into this setting. But slightly more subtle surprises come up if we try to think about more subtle operations like extension of the base field. Okay? So last time I discussed the fact that if I give you k over little k is an extension of non-Archimedean fields, then given any rigid affinoid space over little k, you can cook one up over capital K just by taking the completed tensor product. Okay? Which essentially amounts to saying if you express A as a quotient of a Tate algebra by some relations, this is the same expression except the Tate algebra you take over capital K, but you use the same relations over little k. So this is a construction in the affinoid case. And then if I give you x is separated, well, then you just define sort of the scalar extension by gluing. Namely, you cover x by affinoids, Because it's a separated space, overlaps of aphanoids are aphanoid. The proof is identical to the case of algebraic geometry. And then, since you have this construction on aphanoids and it's functorial, you can show by using the Gerritsen-Grauert theorem it's compatible with open immersions, and therefore you can globalize it and you can define extension of the base field by gluing. And you can even do this for quasi-separated spaces too. But again, if you don't care about quasi-separated spaces, just forget that I said that. So as I said, many basic operations do carry over. There are some little surprises. Let me give you another striking example of a surprise. In algebraic geometry, there's a basic principle that if I give you a scheme of finite type over a field, whatever happens if something happens, if a reasonable property persists over all finite extensions, then it persists over every extension. For example, if you're reduced after any finite extension of the base field, then you're reduced after any extension of the base field. But I'll just say that there are examples, and these are given as an exercise in the notes, of even aphanoid spaces such that if you look at the extension of the base field, that this is reduced for all k over k finite, but not in general. And what goes wrong here, what goes wrong here is kind of hard to articulate. It's just kind of weird. But in this case, what goes wrong is the intuition in algebraic geometry comes from the fact that polynomials have only finitely many coefficients. But these guys are built up out of Tate algebras, which have infinitely many coefficients. And that somehow is why some of these finiteness principles from algebraic geometry, in fact, may and in fact do break down. So you have to be a little bit careful carrying over your intuition. But by and large, things are basically OK. All right? OK, so that said, let's now turn to discussion of slightly deeper properties of rigid spaces. So the next issue I want to discuss are the notions of, maybe cohomology of sheaves, and especially in the context of proper maps, and also in the context of flat maps. But before I do that, does anybody have any questions just about these basic properties of coherent sheaves, or just these basic classes of maps? Yeah?
This thing that is false Euclidean sheaves in general?
Yes. No, that doesn't help because the admissible there's a cofinal system of aphanoids around any point. The problem, all right, I'm about to say something that may kind of not make sense to some people. The problem is that the Tate topos, there are enough points, there are enough abstract stalk functors, but they're not realized by points on the underlying space. So there is a way to make a good theory of stalks, but you can't do it just using this naive notion of stalks at points of the physical space. You have to use a more general notion of stalk. So there's a way to fix it, but it's a little bit technical. Bjorn. Not quasi-separated. So one answer is yes, work with Berkovich spaces, and then all these complications go away. In the general case, there's the basic complication, which is in fact one of the exercises, is that I don't know it to be the case that if I give you an admissible open into an aphanoid space, in which case everything is separated, if you make a massive extension of the base field, if the resulting map is still an open immersion. I don't know if that's true or not. Perhaps it's true, but I have no idea how to prove it. That's the obstruction. So I don't know the answer. Any other? Yeah. Because you have aphanoids, and then their overlap is aphanoid. And so then when you make the base change, the aphanoid piece that they had in common, that remains aphanoid up here, and you'll glue these along that aphanoid. You have a construction first for aphanoids. Now you want to globalize. So the overlaps, hopefully, are also aphanoid, or else you kind of can't get started.
So even if the overlap is a finite union of aphanoids, you still can't play the game?
Yeah, that's what happens in the quasi-separated case. You have to do one thing at a time. Yeah. Any other questions? Okay. Yes, thank you. Sorry, forgetting to repeat the questions. Whoops. Huh? Oh, okay. All right. So now let's go on to the structural properties of sheaves on these spaces. So let's talk a little bit about cohomology. This pen is dying, so let's go to a new pen. Hopefully it isn't dead. There we go. All right, so let's look at cohomology. So, of course, we want to do, well, this came up in Kedelaya's talk yesterday. We want to think about how to calculate cohomology by using something like check theory. So I'll just say that one can show, at least for a quasi-separated space, that the category of abelian sheaves does have enough injectives, so you could think about derived functors, or you could just ignore all that abstract crap and just work directly with check theory. In any event, however you slice it, here's the main theorem. Suppose I give you x. X is, first of all, say x is a rigid space, and f is a coherent sheaf. Then, first of all, if x is aphanoid, then, in fact, the higher sheaf cohomology is 0 for all I. And then, as a consequence of that, by copying the standard whoops, let's try that again, positive I. And then we can copy the sort of arguments from ring spaces that if X is quasi-compact and separated, and U is a finite admissible aphanoid covering. So then the overlaps are also aphanoid, as we just discussed. Then, in fact, there's a natural map from the check cohomology of F with respect to U to the derived functor cohomology of F on X, and this is actually an isomorphism for all I. Okay? So you can really do calculations using check theory, and let me just add as a remark that there is a good theory of what are called Stein spaces. These are spaces which are not, in some sense, too large and are separated and whose higher coherent sheaf cohomology vanishes. The standard non-trivial examples of these are analytifications of affine algebraic schemes. And in fact, you can just take this beautiful book called Theory of Stein Spaces, and you can just take most of the proofs in that book and just observe that they all basically work in the rigid case. Okay? So there are other ways of calculating cohomology, not just using aphanoid coverings, but even using kind of larger coverings by what are called Stein open sets. In any event, cohomology is as computable, well, almost as computable in the rigid analytic case as it is in algebraic geometry. That said, one would like not just vanishing theorems, but also finiteness theorems. And in particular, you might wonder, what about if X is proper? What if X is proper? And then, of course, you're immediately wondering, well, I don't know how to think about that, because what does proper mean? So can we say something about the cohomology of coherent sheaves on a proper rigid space? And so first we have to define what's meant by properness. So how to define proper? So this is a slightly delicate notion. There's not going to be, you're not going to say anything about universal closedness. Okay, that's going to be a very bad notion in this context. So what we're going to do instead is imitate something from the case of analytic geometry. And in fact, in view of the time, let me just say it very briefly. So definition, let me just define it in the affine case, in the case when the base is affine. If I give you a map to an affine base, I say that this is proper if what? If it is, well, it should be quasi-compact and separated, of course. And what I want is that there is a pair of coverings. There's admissible aphanoid covers, V1, Vn, V1 prime, Vn prime of X, such that the ith one of this is contained in the ith one of that. So there's kind of one covering and then a kind of a larger covering. But I want this, in some sense, to sit on the interior of this, to kind of stay away from the boundary with respect to A in the following sense. That I want that there's an embedding of, excuse me, of Vi prime into the base cross some unit ball, such that, which amounts to saying I want to express the coordinate ring of this as a quotient of a relative Tate algebra over the base ring, which I can certainly do, but I want to put this in here so that this smaller piece stays away from the boundary of the ball, such that Vi, so this is supposed to be open, so that Vi sits inside of this base cross a slightly smaller ball. Okay? This property is what's called being relatively compact. It sort of says if we imagine that we put this guy over the base into a family of disks, that this thing has, in some sense, relatively compact closure. On every fiber, it stays inside of a common proper subdisk. Okay? So if you sort of think about it a little bit, this is actually quite a reasonable notion motivated by the topological case. And I'll just sort of mention the fundamental example is rigid analytic projective space, where you take the VIs to be the unit balls in the standard affine charts, which already are a nice cover, and you take VI prime to be slightly bigger balls. Okay? And so then this condition is very easily satisfied. So this guy is proper, by which I mean proper over the base field. Okay? So that's the fundamental example. And, well, one can define properness more generally. All I'll say is it actually holds some surprises. These surprises are addressed in the notes. And let me just mention in passing that, although it may seem surprising, once you do give the general definition, it turns out to be really, really hard to prove that a composite of proper maps is proper. And in fact, this was not settled in general until relatively recently when Temkin solved it by using Berkovich spaces and Raynaud's formal models. So I'll come to these Raynaud formal models in a little bit. But maybe I just want to mention one non-trivial theorem about proper maps to sort of justify introducing it, which is, again, due to Kiel. This definition is rigged to copy the arguments from the complex analytic case. You can show that if X is proper over an affinoid base and F is coherent on X, then the cohomology modules are, in fact, finite A modules. And in fact, once you have this in hand, then you can actually carry over all the standard, the results from like the end of chapter 3 of Hartshorne about cohomology and base change and results of that type. So suffice to say that once you have this finiteness result, in fact, many of the other familiar properties of the cohomology of coherent sheaves do in fact carry over. And most importantly of all, perhaps for many applications, is I'll just say that the Gaga results of Serre do carry over with essentially the same proofs. The only two differences are that you might have non-rational points in a rigid space. So the Gaga results basically say that, oh, yeah, so maybe I should have mentioned one other example. Sorry, let's just come back to this slide. Another example, if X is a proper scheme, then in fact, the analytification is proper. And this is also, in the projective case, this is pretty easy from this case. In the general case, I think, at least I was thinking about it this morning, I think this is actually not at all obvious, rather hard thing to prove in general. But it is, in fact, true. So those are sort of the basic examples. And from this, you might now ask about relating the maps between proper things and maps between proper things, or cohomology of coherent sheaves here, cohomology of the analytification there. And in fact, it all works out quite nicely. So the Gaga-style results do carry over. The only difference is because you might have non-rational points in the rigid space and point-wise arguments can't be used in the rigid setting, if you look at Serre's proofs, you have to tweak them in a few places to get around this fact, these two issues that don't arise in the complex analytic case. Okay? So that said, the theory of proper maps does have pretty much all of the features that you would want, except to prove some of them, you have some unexpected difficulties. But now those difficulties are all settled, and so the theory really is in quite excellent shape. Yes? Oh, sorry. Closed? Sorry. Is that better? Yeah. That's better. Sorry. I think I said quotient of a Tate algebra, but I wasn't thinking. Yeah. Sorry. Closed immersion. Yeah? Okay. Sorry about that. All right. Any other questions? Okay. Can you see? Oh, yeah, there it is. It's even there. Okay. All right, and one other thing I'll just mention in passing is you can also define and develop a theory of flatness by using flatness for coherent sheaves with respect to maps over Y by using, well, either stalks or sort of aphanoid sections. So the moral of the story is that for coherent sheaves, in fact, pretty much everything that you would expect does carry over. But you have to keep in mind that if you're going to want to study any more general kinds of sheaves of modules, which you have to do if you want to think about étale cohomology, then this naive notion of stalks, like for coherent sheaves, really doesn't work. And in fact, the whole theory of these Tate spaces leads to seriously unexpected complications. And so it's one of the motivations for some of the more sophisticated approaches that we'll be discussing, particularly, for example, Berkovich's theory, is in fact to get a more flexible theory of abelian sheaves where you can work with stalks and related constructions in a way that's much more like in the classical case without constantly getting hung up on the lack of ability to use pointwise arguments due to admissibility problems. Okay? So that said, maybe I should now turn to a couple of questions that one might ask that would sort of highlight some of the difficulties in Tate's theory. So let me pose two questions that we can think about. First of all, if I give you map f from x to y, let's even say a map of aphanoids, and I tell you to say this is a flat map of aphanoids, which you could take concretely to mean the map on coordinate rings is flat, although it's also equivalent to maps on stalks of the structure sheaf being flat. If there's a flat map of aphanoids, then you might ask whether the image in Y is in fact a quasi-compact admissible open. Okay? And likewise, in the same situation, if I give you an extension of the base field of infinite degree, then you might ask whether the induced map is flat. Okay? Here you would expect an affirmative answer because something like this is true in algebraic geometry, but it's very difficult to get your hands on the image, and verifying its admissibility is kind of an awkward thing to do. And in this question here, again, keep in mind, when this is infinite degree, the operation of extension of the base field is a completed tensor product, so it's not a pure operation of commutative algebra, whereas flatness really is a commutative algebra concept in terms of ordinary tensor products. So this is not at all evident how to solve just by some kind of naive method. And there are other questions I would call maybe algebraic questions about rigid spaces that just seem utterly beyond the reach of the sort of methods that are sort of traditionally used in this context. And so to solve these and other questions in the affirmative, fortunately, one has to use other approaches. So these are solved affirmatively by using Raynaud's formal models. So that's what I want to discuss in the remaining time. Okay? So I wanted to explain an entirely different approach to thinking about the nature of rigid spaces and maps between them and coherent sheaves on them, with respect to which we're going to be able to convert with a lot of effort, done largely by Raynaud and others, but they sort of did a lot of effort to actually provide a technique for reducing apparently difficult algebraic-style questions about rigid spaces to questions about formal schemes over the valuation ring, which ultimately can be reduced to problems in algebraic geometry whose solutions are generally known. And since probably I'm not supposed to assume that people know about formal schemes over the valuation ring, let me begin with a little discussion about these kinds of formal schemes. So so this is actually a pretty concrete thing. So R, again, is the valuation ring of K. And let me say that a topologically finitely presented R algebra is an R algebra that has the following form: R squiggly braces, I have to define what that means, x1, xn, modulo a finitely generated ideal, where this thing here, these are restricted power series. This is like the Tate algebra, except integral coefficients. These are power series, summation aj, xj, but now integral coefficients, such that the coefficients tend to 0. Okay? So observe that if I take this guy and I actually extend the base to k, which means I invert my favorite choice of non-zero element in the maximal ideal, well, that just converts this into the Tate algebra. Because after all, if I take something in the Tate algebra and I multiply it by a sufficiently big denominator, I kill all the denominator. Because in the Tate algebra, you might have some initial coefficients that are not integral, but eventually they go to 0. So you only have a few non-integral coefficients, so there's a bounded denominator. So which is to say that if you tensor with k, this really does become the Tate algebra. And then you mod out by these elements. This is k affinoid. Okay? So these kinds of R algebras you might think of as some kind of integral model for a Tate algebra. Okay? And so in fact, we can improve on this just a little bit. Let me make one other definition. If A is flat over R as well, we say it is admissible. I'm sorry, this word is overused, but such is life. And the content of being admissible is that the map to this kind of generic fiber is injective. Okay? So these are going to be the basic building blocks that we want to think about. And observing that these give rise to these kind of affinoids, what we want to do is try to build a geometric theory of what we'll call formal schemes out of these, which will turn out to be some kind of notion of integral model for these rigid spaces. So let me discuss a little bit about how to convert this into some kind of a geometric object, some kind of a ringed space. Whoops, let me get a piece of paper. So let's start with this affinoid out. So let A be one of these nice kinds of R algebras, right, of this type here. Okay? And what we're going to do is, so the formal spectrum of A is going to be, well, two things. The topological space, and let's choose an element pi in the maximal ideal that's not 0. So the underlying space is going to be spec of A mod pi. And then there's going to be a structure sheaf. And what is it going to be? Well, I'll just tell you what it does on what we'll call basic open affines. So let's say if we pick, so this equals what? Let's pick an element little a in here, and let's look at, consider the locus a not equals 0 in here. Okay? So I'm going to define what I'll call a sub squiggly a. This is going to be the p-adic completion of the localization. Okay? So what do I want to, the way you want to think about this is the following. This is the inverse limit of a mod pi to the n a bracket 1 over a. Okay? And so what you've done is you sort of take spec a, you reduce mod pi, look at the non-vanishing locus, and now you start thickening it up. You look mod pi squared, mod pi cubed, and so forth. Topologically, the space hasn't changed. So the underlying open set hasn't changed, but you're beefing up the ring of functions on it. And you sort of take the inverse limit. And this turns out to, again, be a topologically finitely presented R algebra. And in fact, it only depends on this physical set. And therefore, you can associate to this set this ring. And so I'll just put it that way. Let me call this U sub A. And I'll just say that U sub A going to this guy turns out to be a sheaf. Or you can promote this construction to a sheaf on the whole space, much like the way you make the structure sheaf of a scheme. And this is discussed more fully in exercise 3.3.4 of the notes. Okay? So the formal scheme associated to A, the underlying space is quite small, but the structure sheaf carries all the kind of the full complete ring. Okay? So if I call this thing X, then the ring of global functions is again just my friend A. All right? So this is what's called a formal scheme. This is a certain kind of a ringed space, and you can glue these together. And so in general, we're going to think about formal schemes that locally look like these guys. And so that's what we'll call admissible. So an admissible formal scheme for our purposes is going to be a quasi-compact locally ringed space XOX, this guy is a sheaf of R algebras that is locally isomorphic to one of these guys, where this guy is topologically finitely presented and, in fact, flat over R. Okay? So that's what we'll call an admissible scheme. And the reason why these are very interesting is because, well, we have a construction in the affine case. Given one of these formal guys, we can promote it to an affinoid guy. And here's the beautiful part. Inside, I give you one of these basic open affines. If I call this ring A, what does this go over to? When I tensor this with capital K, it turns out to go over to the Laurent domain, like that. So in fact, if you think about this guy is being built from these affines by gluing along basic open pieces, you get the data of affinoids with overlaps that are built up from Laurent domains. So in fact, you can glue and generalize to a construction. Given any x, you can define what you call a rigid space, which is called a generic fiber. It's not really a generic fiber, as I've described it. It's just a construction, but it globalizes this affinoid construction. So associated to any reasonable formal scheme, you can get one of these guys. And I mentioned before, as long as we're working in the flat situation, this ring injects into this ring, and roughly because of that, this turns out to be a faithful functor. Meaning, maps of such formal schemes are uniquely determined by what happens on the corresponding rigid space. Okay? And now you can ask, what kinds of rigid spaces do you get in this way? And can you reduce questions here to questions about this? And that's what I'll sort of end with. So in fact, there's a remarkable theorem of Raynaud. So first I'll mention, as a kind of is actually discussed in the notes as sort of an exercise, that given x, this formal scheme that we have over here, that these rigid spaces that we get, they're quasi-compact and quasi-separated. Or if you prefer, if you take this x to be separated in an appropriate sense, these guys will be separated. Okay? So there are some properties that these have to satisfy. For example, if you take x to be, well, I'll just say formal projective space, whatever that means, projective n space, then the generic fiber is in fact this guy. Okay? So what's interesting about this construction, so there's a remarkable result of Raynaud, which says that every quasi-compact, quasi-separated rigid space, x over k, has the form xk for some x. But it's not unique, and he did much more than this. In fact, you can determine, you can characterize, first of all, moreover, every map between such spaces, between such rigid spaces, arises from a map between such formal models for suitable. So these are called formal models. Okay? So as I said, this construction back here, this really is functorial. But there's a lot of flexibility in choosing the integral model for the given generic fiber. And in fact, Raynaud did something even more remarkable than this, which is he was able to characterize exactly how can you tell when two formal models do give rise to the same generic fiber. And it's described in the notes. And all I'll say is it relates to a certain notion that you want to think of as a kind of a blow-up in the closed fiber. If we think of the rigid space as being kind of like a generic fiber, if you had some operation that looked like a blow-up in the closed fiber, then you would expect it might not change this space. And then it's a remarkable argument, but roughly because of the theory of coverings by rational domains, this kind of blow-up operation does not affect the rigid space at all. And in fact, Raynaud showed it's basically the only ambiguity possible, which is to say any two formal models of the same rigid space, they're sort of dominated by a sort of common blow-up in the closed fiber. And so in this way, you can take questions about these maps and try to convert them to questions about these maps. I'll just mention one of the most striking examples, which again is a quite quite deep theorem that if f is flat, that you can arrange this map to be flat in an appropriate sense. And likewise, and again, this is essentially the content of what Temkin proved, if f is proper, it's actually equivalent to this guy being proper. And therefore, since properness on this side, once it's defined, is trivially preserved under composition, you get the same result on this side. In the case of these flat maps, the questions about images of opens, on this side, the image of a Zariski open is, in fact, again, open, once you understand the nature of these topologies. And by using various results that Raynaud proved about the flexibility in the choice of models, the question I posed at the beginning about image of X being a quasi-compact admissible open in Y, by means of this device, you can reduce it to the question about openness for flat maps in algebraic geometry over the residue field, which is a known theorem. And so you get the result that way. And similarly, this question I posed about if you extend the base field, does flatness get preserved? By using this result, going back and forth, you can reduce the question again to the problem of preservation of flatness over what base over various quotients r mod pi to the n. Okay? So by this remarkable theory of Raynaud, that you can always make these integral models for reasonably small rigid spaces, not things like affine space, you can in fact reduce very difficult questions on the rigid side to question on the sort of side of these integral models. And once you understand the theory of these formal schemes, many of these problems can then be readily solved by reducing them to known results in algebraic geometry. And I just should emphasize, this is not just a convenient device. I mean, it's really not known how to attack these problems within the classical framework. And the last comment I'll make about this Raynaud theory is, although it is extraordinarily powerful, in some sense, you lose more because the integral model is not unique. So you don't even have like an honest space to work with anymore because you can keep changing the formal model. So with experience, you can get used to working with these things, but it's not really the right answer to the question of how do we make a more workable theory of rigid spaces that doesn't keep getting hung up on admissibility problems. So Berkovich's theory does give a better answer to that question at the expense of some technicalities, and so I'll take up the theory of Berkovich spaces in the last two talks. Thanks. Yeah. Yeah. Okay, so the definition of flatness is you would, again, there are several ways of doing it. You could say that every stalk upstairs is flat over the local ring downstairs, or equivalently for every open aphanoid up here that lands on an open aphanoid down here, the modulo of sections is flat over this base ring. So that's the definition of flatness for a sheaf, coherent sheaf, and then similarly, if you just work with a structure sheaf, that defines flatness for the map. And so then you could talk about, like if I give you a proper map in a coherent sheaf that's flat over the base, do you have cohomology and base change and so forth? And you can just take the proofs in Hartshorne and they just carry them over. They just work. So yeah, everything goes pretty nicely.